Good morning, afternoon, evening, or night, folks. Welcome to the law of sines and the law of cosines. So let's remember that for right triangles, we have SOHCAHTOA. Some old hippie caught another hippie tripping on apples. So what's that mean? Sine of the angle is equal to the opposite over the hypotenuse. The cosine of the angle is equal to the adjacent over the hypotenuse. And the tangent of the angle is equal to the opposite over the adjacent. Okay? So this slide's hard to do. We have to see that sine involves the opposite hypotenuse, so red and red. Cosine is adjacent hypotenuse, blue and blue. And the tangent is the purple, purple. Cool. But what about for non-right triangles? Like, what do we do there? Because those happen in the real world all the time. So, like, seriously, what do we do? You could make an argument that you could draw an altitude, okay, to the triangle and effectively split this triangle into two right triangles. And that is a solution, but man, that's going to give you extra work to do. Here's another version of that. Draw the altitude on the outside and then apply right triangle trig, but it's just going to take extra work. So we have these shortcuts in math class called the law of sines and cosines. And in order to use them, the first thing we need to do is we need to figure out a new way to label the triangle. Because there is no hypotenuse anymore, we can't just go with hypotenuses and legs. So what we're going to do is we're going to use A, B, and C for now. It could be any letters, but there is a pattern here that you need to recognize. And that is that the capital letters are for the angles, okay? The lowercase letters are for the sides, and we use A and A opposite from one another, B and B opposite from one another, C and C opposite from one another, okay? So that is how we're going to treat triangles when they're not right, okay? So let's derive the law of sines. I've got that same triangle ABC, and what we're going to do is we're going to draw an altitude in here, and we're going to call it interrobang, because that's one of the coolest things that never gets any attention. Interrobang. It just means like, whoa, with a sort of a question mark. Whoa, okay? Anyway, let's check out this triangle. This red one is a right triangle. Let's solve for the interrobang using this angle B and side A. And the interrobang, that's a sine problem. So the sine of B is equal to the interrobang over A. If I multiply both sides by A, then I have that the interrobang, the height, is equal to A times the sine of B. Okay, let's set that to the side. Let's look at the other triangle on the other side. Again, solving for the interrobang, this time using angle A and side B. The sine of angle A is equal to the interrobang divided by B. We're going to multiply both sides by B, and we have that the interrobang equals B sine A. So now that we have the interrobang equaling two different expressions, let's notice that they're the same thing and set them equal to each other, okay? At this point, if I divide both sides by A, and then I divide both sides by B, I have a really nice pattern. That is that the sine of A over A is equal to the sine of B over B, okay? Let's set that to the side for a second, and let's take that altitude and let's draw it a different direction, okay? So this time, I'm going to take this bottom triangle, and I'm going to use angle B and side C, to come up with an expression so that the sine of angle B is equal to the interrobang over C. Multiply both sides by C, and I get that C times the sine of B is equal to the interrobang. So setting that information to the side, and let's solve for this one more time using angle C and side B. That is going to be B times the sine of angle C. And since they're equal to the same thing, we're just going to divide both sides by B, divide both sides by C, and notice that we have a really nice pattern again. The sine of B over B is equal to the sine of C over C. And we're looking here and we say, hey, this here and this here are the same. Let's bring them together. Boop, there we are. So this is the law of sines, all right? And the most important thing about the law of sines is that in order to use it, you must have opposites. You need to fill in a whole column of this equation that has two equal sides, okay? So it has three sides of this equation. You must have opposites, okay? So you either have to have angle A and the side opposite little a, or you have to have angle B and the side opposite it little b, or sine. You have to have opposites, okay? Cool. Here's another version of the law of sines, and we use this one with the side lengths on top when we're solving for sides. If you're solving for sides, it's way easier to have those sides on top. We use this one when you're solving for angles, okay? When you're solving for angles, use the one that's got the angles or the sines on the top. And if you're solving for angles, remember that means you're going to have to use arcsine to undo sine to get that angle by itself. Okay, so warning, warning, warning. When you have an angle and you have a side opposite that, you're going to want to use the law of sines. But the problem is that if the other side you have is defined as longer than the side that you have, the question becomes, where do you draw that last side? Is it there or is it there? We have this triangle or we have this triangle, and we just don't know which one it is, okay? The law of sines is always going to solve for the acutest angle. It's not going to give you this bigger one, and so you won't be able to tell using the law of sines which one it actually is. And so we call that a shortcoming of the law of sines, and that is why we have the law of cosines. The law of cosines solves that problem for us, okay? So let's recognize what it's useful for. If you have side angle side and you want the opposite side, I'll read the formal. If you have two sides and an included angle when looking for that missing side, this is going to be super useful for the law of cosines. Or if you have three sides and you want to find the measure of one of these angles, let's say you're building a deck for someone and they have a strange triangular piece of their deck, you need to figure out where to set your saw to make these cuts. So that means you need to solve for one of these angles. And the law of cosines is going to be really easy to do that when you have an oddly shaped triangle that's not a right triangle, okay? So back to this one. If we had a rope along here, and let's say it's 200 yards or whatever, and we have a rope along here and we stretched it to both sides of a little pond, right? If we can measure this angle that's in between our ropes, then we have side angle side. And then we have this pond and we want to install a frisbee golf hole right here, and we just need to figure out how long it is so that we can put a sign over here on the tee pad that says, like, this is a 90-yard hole or whatever, right? But the law of cosines is going to be super useful for us. So let's see if he makes it, guys. Here it goes, and boosh! Oh, no, never mind. Those chains do not care. Oof. All right, deriving the law of cosines. We're going to draw that altitude again. This time we're going to call it y because we're trying to be nice, right? No, I'm just kidding. Because we're also going to have an x in this one. And we're going to draw this purple right triangle in here. And we're going to say, what relates x and y and c together? Well, it's called the Pythagorean theorem, okay? So what we need to do is we need to take out x and y and put in all a's, b's, and c's, and then we'll have the law of cosine. So how are we going to do that? Well, the first thing I want to do is I'm going to look at this triangle that's over here and try to figure out y in terms of angle C and, whoops, side B, okay? And so that's going to be that the sine of C is equal to the opposite y divided by the hypotenuse B, okay? If I multiply both sides by B, I get that y equals B sine C, okay? Cool? Now, we need to get x. In order to do so, we need to figure out this dotted line piece here, okay? So this dotted line piece is the cosine of c is equal to this adjacent divided by this hypotenuse, okay? Multiply both sides by b, and I get that this dotted line is b cosine c, all right? Now, we're going to say that that's useful because if I want x and I have a, I can say that a minus the dotted line is equal to x, okay? And so making that substitution in blue, we now have x in terms of A's, B's, and C's, and we have y in terms of A's, B's, and C's. So we can now reapply the Pythagorean theorem, okay? We're going to take out the x, and we're going to put in a minus b cosine c, and we're going to take out the y and put in b sine of c, okay? When I look at this guy right here, I have an issue. This is a binomial that is being squared. The only way to handle that is to multiply the binomial by using a box or foiling or just being really careful. So I like FOIL. Let's write it out. First is going to be a times a is a squared. Outer is going to be a times negative b cosine c or negative ab cosine c. Inner is the same thing, negative ab cosine c. And then last is going to be a negative times a negative is a positive b squared cosine squared c. Special note, when you square a cosine, okay, the exponent goes on the cosine. It's really meaning the same thing as if it were on the outside here, but we put it on the cosine because then we know it is not on the angle, okay? Cool. So writing this out, a squared first. Sliding that up, okay. A squared, good. And now these guys are like terms, so they're going to combine into two of those, two AB cosine C's, and they're negative. And then putting down the last piece. And then also remembering that this squared is applied to the B, and it's applied to the sine. So there we are. At this point, we recognize that over here, we have b squared in both of these terms. And so we can factor that out to right in front of that and write it out. But this is the law of cosines. It shouldn't have any signs in it. So we need to go to a fun fact. If we have a triangle that has a hypotenuse 1 and it is a right triangle with x and y, the Pythagorean theorem applies. If I have an angle as a reference angle, if I solve for x and y in terms of sine and cosine, some neat things are going to happen, okay? So the sine of the angle is equal to the opposite over the hypotenuse. The hypotenuse is 1, so if I multiply 1 on both sides, I just get that y is equal to the sine of theta, okay? And I didn't write it, but I sure should have. Sine of theta right here. Anyway, the cosine of x, that's the adjacent, is equal to, the cosine of the angle is equal to the adjacent over 1. If I multiply both sides by 1, I just get that this leg here is equal to the cosine of the angle, okay? So I can rewrite this Pythagorean theorem. The x is cosine of theta, the y is sine of theta, and this makes for an interesting theorem. We call it the Pythagorean identity of trigonometry, and that is that cosine squared of any angle plus sine squared of the same angle is always going to equal 1, okay? So that means that this whole expression that we have down here that I've underlined is just equal to 1. And there we have it, the law of cosines. So let's bring that up to the top and let's formalize it a little prettier. Here I have a positive a squared and a positive b squared. I'm going to put those together like this, and I'm going to read this out. C squared is equal to a squared plus b squared. What? C squared is equal to a squared plus b squared? Minus 2ab cosine c. You guys, that first part is the Pythagorean theorem. today you get to learn the big brain version of the Pythagorean theorem. This part's always there. We just don't always write it. And why don't we write it? Well, that is because the cosine of this C, if we put the capital C at the right angle, cosine of 90 degrees is equal to 0. So if I substitute this cosine of 90 right there as 0, 0 times negative 2ab cancels out. And we are left with just the c squared is equal to the a squared plus the b squared, okay? So this is the hidden part of the Pythagorean theorem that you only get to learn once you're at a high enough level in math class, okay? And that's pretty special. So there are 3 other versions of the law of cosines, okay? And I know they look super scary, but notice this pattern. If you're looking at cosine of capital C, the only other spot that C is found is on the other side of the equal sign, okay? So those are opposites. And then this A and this B and this A and this B, the order here does not matter because it's a product, and then the order over here does not matter because it's a sum. So you just have to remember this piece about the opposite sides of this, okay? If you're looking at angle B, the opposite side of the equal sign is going to have the lowercase b. Okay, if you're looking at angle A, the opposite side of the equal sign is going to have the lowercase a. Okay, let's see how this works for finding the distance across that lake. And how easy this formula is. Okay, so first thing I'm going to do is I'm going to take out C and I'm going to call it theta. I'm going to take out the A and the B and I'm going to call them adjacents, okay, because they are next to the angle. So we effectively have a side followed by an angle followed by a side, or side angle side. Okay, I'm going to substitute that information up into the law of cosines, and then I'm going to say, how hard is this to solve for the question mark? It's being squared, so square root both sides, and there we have a missing side of a triangle. When you have side angle side is equal to the square root of the adjacent squared plus the adjacent squared minus 2 adjacent times the cosine of the angle. And keep in mind, these are interchangeable and these are interchangeable. The order there does not matter for the formula because of PEMDAS, or PEDMASA, sorry. All right, and if you have 3 sides and are looking for the measures of the angles, okay, I'm going to take out the question mark, put in a C, and then we're going to solve for the capital C. Right now that term was negative, so I added it to both sides, and now it is positive. I'm also going to take the c squared and subtract that on both sides, okay? Let's clean this up. We have 2ab cosine c is equal to a squared plus b squared minus c squared, okay? We're going to take this 2ab, which is multiplying by my cosine, and I'm going to divide both sides by 2ab, okay? Now I have that the cosine of the angle is equal to a squared plus b squared minus c squared all over 2ab, and we must arc cosine or inverse cosine in order to cancel out that cosine and get c by itself, okay? I know that this looks like an incredibly crazy formula. Notice that we're taking out the c, putting in a theta. We're taking out the a, putting in adjacent, taking out the other b, putting in adjacent, and taking out the c and putting in opposite. So what does that mean? Ooh, it looks so scary, except for that it's not, okay? Because when we're solving for an angle in a triangle, the thing you need to remember is that it's the arc cosine of the sum of the squares of the ones that are next to minus the square of the opposite. In other words, guys, when you use this formula, the one that's being subtracted on top, it's the only minus sign in this problem. It's on the opposite side of the triangle from the one that you're getting, okay? And then these remaining pieces, they're copied right here, but the order does not matter because the order of addition does not matter and the order of multiplication does not matter. So this is a super useful formula, okay? And here's a GIF demonstrating what happens when you have angle, side, side. You just don't know which one of those triangles it is going to be. And the law of cosines, if you use it, you're going to end up solving for this remaining side, but it'll be a quadratic that you solve. And a quadratic will give you 2 solutions. a longer one, and a shorter one. Okay, so let's see here. English is important, but math is importanter. Awesome.